This is the apparatus with which I wish to show the fact that the amount of time force is applied affects the change in momentum of an object. So I have a cart which is connected via a string to an accelerating mass over a bench pulley. The light gate is there in order to do the recording of the time. Now if I have a look at the rear of the cart, you can just about make out that there is a optics pin stuck to the back, and that is designed so that when I pull this back and it reaches a predetermined mark, it is just clearing the floor. It is just touching the floor. By sticking this on, I can now move the light gate, and there is a light that comes on. I want it just to come on. In fact, I just want it to go off as it's moved away from the position there. So that is set up so that at that zero that it is freestanding. This reduces any time of passage where the cart is undergoing friction without any acceleration. Here I'm using a mass to accelerate the cart. The mass is being accelerated by gravity, but it is not the total mass of the system. In any case, the total of the mass of the system remains constant, so that the SUVAT equation, S equals ut plus half at squared, still holds true. If you look at the equation, you can see by rearranging it that you can make the time a function of the height held. So let's get some data. First thing to do is to bring the truck back. And I'm moving the so 2 centimeters. So I'm checking for parallax, and it's exactly 2 centimeters off the ground, and I release, and it gives me a value of 0.455 meters per second. I now move, making sure that the string goes over the pulley to our second marker, which is the 4 centimeter mark. Check for parallax and release 0.565 meters per second. Again, putting the string over the pulley, avoiding the light gate on the way back. 6 centimeters. Checking for parallax. And release. 0.645. Just making sure that the marker is in place. I am at 8 centimeters away. The marker is in position. .718 meters per second. do it around the cameras, not so easy. 10 centimetres. The shadow's making it awkward. 0.789 meters per second. Twelve centimeters. 0.846. Of course, I'm only going to do this once, but in a class practical, you'd probably want to do this 3, maybe 4 times. 14 centimeters. 0.899. So all the time this is being accelerated, it's 16 centimeters. All the time this is being accelerated, the mass remains constant. You've got the accelerating mass is, as I said, 200 grams, but something of the order of about 700 grams total. So not all the mass is acting under gravity. So 0.972 meters per second. I have done this before using using cotton thread as the instead of string, but I noticed that did tend to twist and effectively change the length of it. So that if you're going to use string, please make sure that the length remains constant. That was 18 and it's 1.009 meters per second. And the last one I'm intending to do is 20 centimeters, which is 1.053 meters per second.